amino acids, right? And we talked about the review type process when we ended up class last time, which is, we could take an amino acid like this, and then we could go through a process where we did the BR2 and PBR3, right? That's the Hell-Volhard-Zelinsky reaction. And then once we brominated it, right, then we could add in the third step the amine, right? And that will give me an alpha amino acid substitution. And again, that's pretty well reviewed. We've done the Hell-Volhard-Zelinsky reaction, and we've done a nitrogen substitution. We also have a couple of new synthesis that we need to look at. Adamine monalate. I can never say that word correctly. Okay, this is very similar to the malonic ester synthesis and our acetoacetic ester synthesis. It starts with a diester compound with an amide attached. So here in the alpha position, we have a amide. Okay, so that's the amidomalonate compound. And so like with our acetoacetic ester synthesis or the malonic ester synthesis, we react this with first our base that makes our enolate. And then second, we'll have that react with an electrophilic group. That now attaches that new R group. We still have our amide there, and we have the two esters, right? So all we've done is deprotonate, right? We pulled off that proton right there. And then if we react this with acid and heat, that's going to take this to the racemic amine, and most often shown this way. So the first one, that's very much like our malonic ester, but this last one, we have several things occurring when we add the acid and heat, right? It looks like magic. So we need to think about, first, we're going to hydrolyze, right? And we got two different groups to hydrolyze. We're going to hydrolyze the esters, right? And we're going to hydrolyze the amide. Okay, so that acid and water are the right conditions to hydrolyze both sides of the ester and our amide. And then with the heat, right, we're going to decarboxylate. So if we look at the process here, oh, I meant to show the middle process and I went all the way to the end, sorry. So what happens with the H3O plus, right, is that we get the hydrolysis, right? So we turn both of these into acids. right? And we've already at this time lost that bottom carbonyl down here, right? And then from here, right, we decarboxylate. Questions about this one? This, like the earlier one that we looked at before, this is racemic. And again, if we remember our carbohydrates are always stereospecific, so are our amino acids. Yes, ma'am. In the acid conditions, really they would both be the positive, right? You'll see in the book that it'll show it with just the NH2, but under strong conditions, you would end up with the protonated nitrogen, and then you'd have to neutralize it to get it to the neutral form. But yeah, that was inconsistent. Thanks for catching it. Okay. The next synthesis we have for amino acids is a striker synthesis. This one starts with an aldehyde. Reacts with sodium cyanide in ammonia, so ammonium chloride and cyanide. So this is producing the hydrogen cyanide in situ. This does two things at the same time, right? We're going to replace our oxygen with that nitrogen, and then we get the cyano group attached. If you think about this, you can think about it kind of going in two phases. Right, so if we had a mild acid solution of ammonia, right, we could form the imine, and then the imine can react with the cyano group. Once we have this, all we have to do is hydrolyze it to get to the amine. And again, this one is going to be racemic. Questions about this synthesis? So this one uses some older chemistry, right? We know how to make imines, and we know that cyano groups will react with carbonyls. They'll also react with imines, and then we just do a hydrolysis, so the striker synthesis. One of the things we didn't talk about last time in detail that I think is important to talk about, you'll talk about it quite a bit in biochem, so we're not going to get in depth, but is the fact if we look at an amino acid, and this kind of gets to the question before about how do you show this, is that if this was in a neutral pH, the correct way to show this is actually as the zither ion. So in a neutral pH, the acid actually is anion, right? And the base, the nitrogen, has the proton, right? So this is your different solutions. Now, as we acidify, so if we think about this being kind of the neutral species, you're going to have several possibilities, right? You've got the possibility of going more acidic. And I dropped my positive off of that, so make sure you get that, right? And having this species, right? So under higher acidity, we'd end up with this species, but you also have the possibility of having and I'm going to turn that around a little bit. Go this way, which means for amino acids, you're going to have a pKa 1 and a pKa 2. So when you get to that, you'll see this terminology of the pKa 1 and pKa 2. And that is going from the anion to the neutral zwitterion species, and then protonating that again to get you to the positive species. Because of this pH 7, you're going to see often when you get to biological classes and the biochem, you're going to see the zwitterion drawn quite a bit. Okay. So if we look at peptides, the next step, so we're going from amino acids to peptides, and then we'll get the proteins. Go back a little ways. So when we look at peptides, really what a peptide is the peptide bond. But really, what is this peptide bond? What would I call this functional group? Anyone? Carbonyl with a nitrogen attached? It's an amide, right? We covered that in the carboxylic acid derivatives, right? So what a peptide is really just a polyamide. And the peptide bond is just that bond right there, right? That's the peptide bond. Right, so peptides are going to be polyamides. If we think about an amino acid is going to have an amine and a carboxylic acid, which means that now it can make these chains, right? So you've got these long chains made of amino acids, right? And if we think about, we have 26 natural occurring amino acids, everything naturally occurring is going to be made of these 26 amino acids, right? In different forms. So if we think about when we talked about DNA, right, we had 4 base pairs, right? And those 4 base pairs then coincide to the RNA 4 base pairs. And then those RNA are the messenger RNA that goes into an enzyme that then communicates the synthesis of proteins, right? And the protein is made up of these 26 different amino acids, right? So whenever you're talking about polypeptides or peptides, right, remember that's just amides. It's a different word for the same thing. So when you go into biochemistry or in biology, it's just an amide, right? So why do you have acid in your stomach? So whenever you eat proteins, either vegan proteins or dairy proteins or meat proteins, right? What happens? Gets in your stomach, it's acid and water. What happens to amides in acid and water? They hydrolyze, right? So once they hydrolyze, it turns from protein into little bitty amino acids that can go through your blood cell, your membranes, right? And go into your bloodstream, and then they can go in and get absorbed into cells. And what does your cell do with it? Whenever it gets a message from that messenger RNA, then it turns it into more proteins, right? So think about it as a bunch of Legos that get flowing around and you just keep building things with them, all right? So this is peptides are just polyamides. Proteins are, of course, polypeptides. And a couple of specific things about proteins that I want you to take away from if you take biochemistry, you'll get into this in much more depth. But first, we need to understand the structure. And there's 4 phases of structure. We have primary structure. The way to think about this is the linear structure. Okay, and here amino acid 1 is attached to amino acid 2, it's attached to amino acid 3, is attached to amino acid 1. It's just what are our amino acids in a linear form. Our secondary structure is the 3D conformational structure. So if we go back to our Newman projections, right? And we've got eclipsed and staggered forms, right? And so you've got these different forms. Whenever you have an amino acid, there's going to be a natural 3-dimensional conformation for that amino acid. And when I connect that amino acid to another amino acid, now you're going to have 2 3D conformations interacting with each other. And so the 2D structure is just going to be the lowest energy structure for that, right? And so therefore, it can form different things. The 2 most common, and they can have different sizes based on the amino acids, is the alpha helix, right? And the beta pleat, or pleated sheet. When we get to the 3rd structure, this is the 3D shape. And this one has to do with the folding, right? So as the protein is going together in the enzyme that's creating the protein, it's going to have a very definite shape, right? And that shape of that protein as it is going to be, that folding of that protein is going to be 3D structure. It turns out if we take that protein and we either add heat or acid, or sometimes there's other things we can add to it, heat and acid are the most common. What we can do is change that 3D structure. This is referred to as denaturing. Okay. Has anybody ever cooked an egg or watched an egg get cooked? Right? The egg, when you start out with it, is pretty well transparent. But what happens whenever you cook it? It becomes the egg white, right? It becomes opaque. What's happening is as you're cooking it, either with acid, not many people cook eggs with acid, but you can, or with heat, right? What's happening is you're denaturing the proteins, which is you're taking their normal folded and you're having them go out. What happens is because they have kind of a folded nature and they're kind of just becoming strings, that's why it goes opaque, right? Same thing happens with meat, right? When we cook it, ceviche, you do that with acid, right? Put lemon juice on fish, right? And you cook the fish flesh, and it's the acids that are doing the denaturing, right? So One of the things can happen in the human body is as you start to get hotter and hotter, there is a point where heat can actually kill you, because it gets to the point where you start to impact certain enzymes folding, right? The three-dimensional nature, to where they can't do their job anymore. So there is heat stroke, which is usually what happens, but you can actually get to the point where you get so hot that it can kill you, right? Heat stroke is the way that most people die of heat, but you can even go past that. And well, it's changing the denature. The fourth structure, quaternary structure. Is when you have two or more proteins that come together to make a structure. So if we think about ATP synthase, that's it's 29 or more. 29 popped in my head as soon as I said it. But that structure, if you've ever seen the molecule, if you haven't, go look up ATP synthase. That's made of lots and lots of proteins, right? And those proteins all come together to create that enzyme. Anytime you hear synthase, that's usually going to be a protein. I mean, an enzyme. Okay, so if we look, did I not download that picture? I don't know where it went. Okay. Well, it's here. So we'll look at it here. So if we look at it, this might help a little bit better, as you have to go and look at my kids' pictures all the time. Let's see. Let's move it over here. Oh, that's small. Okay. So if we look here, right, a primary is just going to be the sequence of amino acids. When we get to the pleated sheets and the alpha helix, right, we get to the proteins, protein structures. I'm sorry, let me fix this. Get the protein structures, right? When we get to the tertiary, this is the folding, right? And then within that folding, you have your secondary structure. And then we only have quaternary structure when we have more than one amino acid, here shown by two different colors. Questions about protein structures? The other thing that we need to look at is protein function. We have structural proteins, enzymes, and transport. With structural proteins, these are things like the alpha keratin, right? That makes up hair, nails, skin, right? So proteins can be most of our structural You do have some things like forgot it. It was in the last chapter. We didn't cover it. Enzymes, right? These are our catalysts. If we think about that folding and that structure of an enzyme, what that's made to do is to usually take a molecule, right? Hold that molecule and have another molecule react with it. There may be acid units within that enzyme, but each enzyme is made to do a single purpose. And it is usually, and most often that purpose is going to be chiral, meaning only one enantiomer, right? So enzymes are very, very specific. Now, there are times when there was a question about how you get cancer from different things. There are things that will mimic other things. That's how drugs often work, right? If we can get a drug that will mimic the shape and responsiveness to, let's say, an enzyme for pain, a pain receptor, right? What that's doing is we're taking that drug and we're putting it into that hole, that enzyme cavity, and then it is acting like that, right? And so there are times where we can mimic the structure. The other thing scientists are now starting to do is to create synthetic enzymes that can be used to make those molecules. So we can take a bacteria, we can change and put a synthetic enzyme in it by coating it in RNA, and then we can actually use that bacteria then to create optically active, meaning enantioselective pharmaceuticals with that bacteria, right? So you're using it as a little factory. And then transport, the example here is like hemoglobin. Right, which is actually a protein, and then the heme molecule, which has the iron center in it. We're not going to have enough time this semester to go in depth in lipids, but it is important to go ahead and just talk about lipids. So if we think about the main three bio or organic molecules, you've got the carbohydrates, you got the proteins, which is based on amino acids, and then you got lipids. Many of your lipids are just long chain fatty acids or esters, right? So a lipid can be a long chain fatty acid. A lipid can be something like our hormone species, right? So estrogen, testosterone. And it can be some of our smaller molecules, like not are similar, but not exactly the same. So lipids, often we think about lipids as fats and oils. Fats and oils are both these compounds. And then we have our prostaglandins, which are often things like hormones. They're things that are going to be messenger molecules that can turn things on and off biologically. And then you have another group that aren't more or less biologically active, but synthesized by the body. So we're not going to cover lipids in depth, but it is important for you to be able to recognize lipids. Your biochemistry instructor won't expect you to know everything about lipids, but would have hoped I at least covered that much, that you know what those are. Anybody know the main difference between a fat and an oil? Good point. Saturated versus, and that's sometimes true. So if we look at a and I'll make sure I use a cis and not a trans, right? This would be a saturated. This would be an unsaturated. So this would be a saturated fat. This would be an unsaturated fat. Whether it's a fat or an oil depends on actually its temperature that it changes. So at room temperature, is it a solid, or is room temperature, is it a liquid, right? Now, whether it's saturated or unsaturated, that's a chemical difference, right? And things that are saturated tend to be fats at room temperature, and things that are unsaturated because of their bending, especially polyunsaturated. And I'm going to try and make all of these cis and not trans. The polyunsaturated tend to be oils. But that's because polyunsaturateds have lower melting points than saturated. And all naturally occurring double bonds in unsaturated and polyunsaturated are cis double bonds, not trans. Once you make a trans double bond, it doesn't react the same way. And if we think about this, this makes a lot of sense. If I have a cis double bond versus a trans double bond, and I have an enzyme, right? If all naturally occurring double bonds in lipids, right, are cis, and my enzyme is made to fit a cis, what's the problem with the trans? The geometry is all wrong, right? I've got something that more looks like this and can fit into that hole, and now I'm taking something that looks like this and it can't fit in that hole, right? So that's one of the reasons that trans is not as more problematic, right, than even unsaturated fats. Okay. All right. Okay, so we covered that. Let's go ahead and do some try this, get you ready for the quiz. And on Thursday, we'll do some try this off the new stuff. I'm going to focus on some of the things that might be on the quiz in the next few minutes. So let's take a little bit of time and try these three. Let's take another 30 seconds. Feel free to talk to your neighbor about the answer. Look at your notes if you need to. Okay, let's take a look. Okay, so remember we started in aromatic, so aromatic electrophilic substitutions. Here we have a Friedel-Crafts. Acylation. So this is going to the acid chloride is going to work with the aluminum chloride to create the acylium ion, which then will react with the benzene, okay, to give me the carbonyl. This next one here is a Diels-Alder reaction. Diels-Alder reaction is a 2+4 paracyclic type reaction. So remember, that's going to go in a circle, paracyclic reactions from chapter. This one, the diene is symmetric. So therefore, I only get one possible product. And then the last one again is an aromatic electrophilic substitution. Here I have a substituent, so I need to think about what? I need to think about the directing effect, right? And this one is an ortho paradirector, right? And so I could get the ortho. And is the methoxy really bulky? No, it's there, but it's not really bulky. And so the ortho would still be a possibility. Questions about these three? Okay, so review all your aromatic electrophilic substitution reactions, right? There are always pairs. What will become your electrophile and then the activating group. And look at your directing, right? So make sure you go back through and look at all your ortho paradirectors, your activators and your deactivators. Remember your Diels-Alder reactions? That's our main paracyclic reaction. It has both stereo selectivity and regio selectivity in the Diels-Alder reaction, so make sure you look at both of those. Let's try a couple more. Let's take a little time with these. Give me the reagents necessary to do these transformations. Okay, let's take a look. Okay, whenever you're doing these reactions, it's always good to go ahead and do several things. One is to think about what's happening. Right, in this first one, we have an oxidation. In the second one, we've replaced the oxygen with the nitrogen, right? We're going from a ketone to an oxime. In the last one, we've got an aldehyde, and we're going to a cis alkene, right? So it's think about what's happening in each of these cases. In this first one, we're oxidizing the aldehyde, right? But could we oxidize the primary alcohol to an acid? Yes, that's also a possibility. So what we want here is to make sure that we use the right reagents, right? And PCC will stop at the aldehyde. We could have also used Swarn oxidation. PCC is the one we've been using most often. Here we have a ketone going through the oxime. Right? We know that we can replace carbonyls with nitrogen, and then whatever is attached to it goes along with it. So NH2 is our main part, but then we could have an R there, we could have another hydrogen, we got an OH, and then we just need a trace of acid. Usually shown with the brackets around the H plus. This last one, this is a Wittig reaction. I know it's a Wittig because I have a cis, and so this is going to be the, and then we just need the right number of carbons, right? So that's an unstabilized phosphorus ylide. That will give me the cis alkene. Questions about these aldehyde and ketone reactions? There's a lot of these reactions, right? So make sure you start to review these. Let's take a little time. Again, feel free to look at your notes. Yeah. Yeah. Okay, let's go ahead and take a look. Okay, if we have an anhydride or a chloride, remember that all we need to do is add the group that we want to add. We don't need anything other than either the alcohol, water, or amine. And so in this case, we've added the methanol. So what's going to happen, the ethanol. So what's going to happen is I'm going to turn that into the ethyl ester. Now, once I've done that with the other side, the other part of this, right, would just become the acid. Here we got the second one. We have the chloride. Again, the chloride is very reactive, so we don't have to worry about adding acid or anything to promote this. And so adding the excess of the amine will give me the amide. Going back to chapter, back to our aldehydes, right? If we add an aldehyde with an alcohol and a little bit of acid, we're going to form the acetal. Questions about those three? Some of this starting to come back to you. Let's try some more reagents. Okay, let's take a look at the first one. And the first one, we're going from an acid to a chloride. If we remember our reactivity or of our acid derivatives, the acid chloride is more reactive than the acid. So therefore, we're going up in reactivity. So therefore, we need a special reagent. And so the one we have for this is the SOCl2. Sometimes shown with pyridine, often for the acid of the chloride, not shown with pyridine. The next one, we're going from an amide to an amine. Right, this is a reduction. So to reduce, right, we want a reducing agent. Lithium aluminum hydride works for this one. Sodium borohydride would not work. So for our acid derivatives, we need the lithium aluminum hydride. This last one is moving up a couple of chapters, the last test. Right, well, we're going to end up here. We've got amine and acid, which means the first thing we're going to do is form the enolate. Once we have the enolate, it can react with another aldehyde. But since S has heat, right, and the base, we're going to end up with the alpha beta unsaturated. Questions about this one? Let's try a few multi-step. Take a minute or so on this one. Yes, ma'am. On the quiz, on the final, there'll be a mixture. There'll be a mixture, yeah. You'll have some multi-step on the final. Yeah. On the quiz, it's going to be most often single step, unless it's something like the lithium aluminum hydride where it's 2 steps always. Whenever you see a synthesis like this, always try and evaluate it. Okay. This bond here, right, seems to be the bond we're making, that carbon-carbon bond we need to focus on. Right? So if we think about that carbon-carbon bond, that appears to be just a Friedel-Crafts isolation. Well, except I put too many carbons. And that forms my carbon-carbon bond. Now, why did I not add the amine? What would happen if the amine with the aluminum chloride? The amine would have reacted with the aluminum chloride, and that would have been a problem. So we're going to do this stepwise. We're going to make the carbon-carbon bond. Then the next thing we need to do is focus on the transformation. So now what I need to do is add an alpha amine. Do we know of a way to add an alpha amine? No. Do we know how to add an alpha halide? Yes, right? So at this point, we need to add an alpha halide. We only have one alpha position, right? So therefore, Br2 in mild acid. That adds the bromine. Once we have the bromide, we just need a nucleophilic substitution. So add the amine. It's a good nucleophile. Here, you don't have to put this, but I'm going to write a note. Right. So here, if you have excess of amine, but if you have any acid, you'd get competing reactions. So you want to make sure you had no acid here. What would happen if I added the acid? Right, you could get both the imine and the amine. And if you added water and acid, you could go back. Right, because you can hydrolyze imines. Questions? When you're doing this, even though the final exam's probably not going to have more than a few multi-step syntheses, it's a great way for you to review. The reason it's a great way for you to review is it makes you recall multiple reactions at one time. So practice using the multi-step synthesis because it's going to help you recall these reactions, right? And at this point, we have all the reactions available to you. So there's lots of possibilities. Okay, let's do one more and then we'll call it a day so y'all can go get ready for the quiz. And again, it's going to take several steps. Okay, let's go ahead and take a look. So if we look here, we have two carbon-carbon bond formation. We have one that's going on the beta position and one that you can consider going directly to the carbonyl. So when we have two, we need to think about when we're going to do them, right? If I did the direct addition first, then that might actually complicate the beta addition. So what I want to do is do the beta addition first, and then I'll focus on the second carbon-carbon bond forming reaction. After we add the second one, you'll see why that's a complication. So to add a beta, what we want to do is add our Gilman, right, which is our copper reagent. That's going to do a beta addition. We lose the alpha beta unsaturated, but we still have the carbonyl. To do the direct, now we're going to use a Grignard. Okay, so get 4 carbons. And notice that after the direct addition, right, I actually convert my carbonyl into the alcohol, right? Because the Grignard is directly attacking the carbonyl. That leaves me with the OH. And then how can I get from the OH back to the carbonyl? Well, this is just an oxidation, right? I need an oxidant. Does it matter which one I use? Can I over-oxidize this? Only if I do the Baeyer-Villiger, which is the peroxy acid. So here I could use the sodium dichromate, chromic acid, right? Or PCC and methylene chloride. So any of my oxidants will do this. Right, so taking a secondary alcohol to a ketone, any of my oxidizing agents can do that, okay?